In this clip, we're going to do an example calculation for finding the surface area of this function here, x squared minus 3y plus 3, over this domain where the absolute value of y is less than or equal to x, and x ranges from 0 to 4. So let's see. So first, it's always nice to get to be friends with your domain. So let's draw a little picture of the domain and see what's going on. So we've got x is going to be ranging from 0 to 4, so we'll call this 4. And then we've got the absolute value of y is going to be bounded by x. So let's see, so if we draw the boundary, there's y equals x. And okay, so it looks something like that. And then we've got this region demarcated like so. So we're going to be doing the integral over this triangle. And if you were wondering how I got this region, or if some part of that didn't make sense, remember that when you're trying to figure out where something is, you can always evaluate a point. So for instance, if I take a point right here, I can see that the y-coordinate is definitely smaller than the x-coordinate, and so that means I'm in the right place, so that point is included in the region. Okay, so there is our region D, and let's see, so we know from the previous clip that dr is going to be square root of the x partial squared plus the y partial squared plus 1. And it's easy enough to compute the partials for this one. So we get 2x squared plus minus 3 squared plus 1, which simplifies to, what do we have here? 10 plus 4x squared. All right. So now, in order to figure out what the area is, it's going to be the double integral over the parameter domain of our area element that we just found here. So 10 plus 4x squared dA, that's our surface area element. For this particular function. And so let's see, so now if we set this up as integral with respect to x first, like so, then all hell breaks loose. So this is not pleasant. This is going to require integration by parts. We're going to need to use the inverse hyperbolic sine function, and we're going to have to set it up as two integrals, because when you look at our bounding curves, we've got one lower bounding curve for these integrals and another lower bounding curve for these integrals. So that's just all kinds of let's don't do that. Back up. Okay, so let's do it instead as the integral, and so let's see, so from 0 to 4, and from minus x to x, and then we've got our 10 plus 4x squared, that's dy dx. So back in our figure, we're going to go that direction first, dy. If you were wondering where I came up with this integral from minus x to x here, that's exactly coming from this part of the bounds right here. This can be rewritten as minus x less than or equal to y less than or equal to x. So that's telling you exactly the range of integration for when you do the dy integral. Okay, so that's where that came from. Let's see. So then this is going to be, let's see, doing the y integral, I can go 0 to 4, and I can pull out the 10 plus 4x squared outside, and then I have the integral from minus x to x dy, and then dx. And then notice that I cannot pull this guy out because it depends on x's. It's got x's here and here, and this is an integral dx, so I cannot pull it out. I have to do it in place. So instead of rewriting the whole thing, no, I'm going to do the inside calculation on a piece of scratch paper. And I see that it's going to be 2x. So this is integral from 0 to 4, my buddy, the square root times 2x dx. And let's see. Now I can solve this one with a good old u substitution. So let's take u to be our 10 plus 4x squared, and then du is going to be 8x dx. And I've already got a 2x dx in there. So if I divide both sides by 4, then this is going to be my 2x dx, which I have right here. And so then, this part here is going to be my square root of u. So this becomes integral of u to the 1/2 times 1/4 du. And let's see, so when x is equal to 0, u is equal to 10, and when x is equal to 4, u is equal to 4 squared is 16 times 4 is 64, plus we get 74. Ooh, all right, and now I will go ahead and integrate this sucker, and we have, let's see, u to the 3/2 divided by 3/2, so that's times 2/3, and I've got a 1/4 out there, and this is evaluated from 10 to 74. So this is going to give me 1/6, and then I have 74 root 74 minus 10 root 10. And I guess if you want to be fancy, you could cancel the 2 out of there and have that be like 1/3, 37 root 74 minus 5 root 10. But I mean, whatever. Good enough.